first speaker this morning is Tim Gowers. At the dinner, I mentioned that at the first Big Proof meeting, I was disappointed that there wasn't that much involvement of mathematicians. It was mostly people already working in the area interacting with one another. But Tim was very much an exception. Tim spoke in a workshop and on a panel. But during the 6-week period, he was just constantly around. He gave seminars and just discussions and interacted with people. Tim has long thought about how human beings solve problems, or how talented and capable human beings, how we should solve problems, right? How we solve problems when we solve problems in mathematics effectively, towards thinking about how that can be mechanized. And those ideas and insights have been a great benefit to the community. But also his involvement and interaction with many of us thinking about similar things has been a constant source of encouragement and support. So we're grateful to that, and I'm looking forward to hearing what you have to say.
Thank you very much. Right, so let me just, I actually managed to find a video of a talk that I gave as part of the sort of more general Big Proof meeting in 2017. And I want to reflect a little bit in this talk on how the world has changed since then, or more precisely, since lots of people have reflected on that already. I don't want to repeat all those things, but just how my concerns and ambitions in this area have adapted to what's been going on. So, let me just lost the clicker. It was here somewhere, but for the moment I can do without it. So I want to talk about human-oriented automatic theorem proving. So if you'd asked me back in 2017, I would have contrasted, and this was a sort of common thing to do, to contrast human-oriented automatic theorem proving with machine-oriented automatic theorem proving. And the rough idea was that for human-oriented automatic theorem proving, you investigate as well as you possibly can how human mathematicians find proofs.
Find the official one. You just have to plug this. Maybe you have no USB port.
Perhaps this is it.
Yes.
Okay. I'm still showing my age. I'm sure I wouldn't have done that back in 2017. Anyway, you sort of look at how humans find proofs, and you understand that well enough that then you can automate it. And that's still what interests me. I still spend quite a lot of my time proving things that I don't know how to prove, finding exercises or competition-y problems and things like that, and trying to keep a close eye on what I do in order to prove it. And I should mention, well, I'll mention that in a minute. Now, I'm sure a lot of people here are familiar with Rich Sutton's bitter lesson, saying that that approach, was completely not the approach that worked for chess. What worked for chess was just scaling up your computers until they could do lots of brute force searches, and they became much better than humans. And you're supposed to generalize from that to all domains, that you shouldn't bother to sort of really try to understand what you're doing. And I've never liked that, and it's not clear to me that it really does generalize to mathematics in particular. And another thing that I wanted to contrast myself with then, was with formalization. So we heard a lot about formalization. For me, I'm very, very happy that all that's going on. And I really hope that we will get to a stage quite soon where it will be possible, because of all the work that lots of people here are doing, for real mathematicians, for mainstream mathematicians who haven't learnt Lean or Isabelle or whatever, just to sort of type their thoughts in a reasonably formal way, have it auto-formalized, and so on and so forth. And I think that could be a really incredible benefit. But it's just not what I'm personally working on. But of course, the big thing that's happened since 2017 is a huge explosion in machine learning. And now we've got another sort of aspect. I mean, I want to contrast myself a little bit with that. So what would be the contrast? I think in machine learning, there's a sort of ethos that it's really nice if you can somehow, quote, solve mathematics, unquotes, without actually really understanding how people do mathematics. You just want to come up with the right combination of machine learning ideas. You do some experiments, and with any luck, you absolutely ace some benchmarks or something like that, and then there you are. I want to argue a bit that there's still value in actually trying to think about how we ourselves solve problems. I mean, the short reason for that would be, it's clear that we're still, for the problems that we manage to solve, doing it in a much more efficient way. We're doing much less search, and if we can somehow understand why we're doing much less search, then there's the potential to make computers far more efficient. So back then, so here are the things that I've worked on over the years. So I worked on so I had the good fortune that an amazing multi-talented person, Mohan Ganisalingam, he was very, very good at mathematics and computer science and linguistics. So it's a really useful combination of skills. And with him, we developed a program that could solve problems. So this with no backtracking is an important part here. So it could solve problems in reasonably abstract sort of metric space theory and things. Problems that we sort of defined routine to mean a problem that a human would solve without backtracking. You just do what seems like the obvious step at each stage and get to the solution. And we wanted a computer to write a program that also would do the step that seemed obvious to a human and wouldn't sort of search through lots and lots of silly steps in order to find a good step. In the end, it turned out that what our selling point to the wider community wasn't really that. It was more just the fact that we, which wasn't actually that hard to do, got the output. Because it was doing it in a sort of human type of way, you had a kind of one-to-one correspondence between its thought process and what a human would write. So it was possible to convert the output of this program into sort of natural language text in a purely mechanical way, and get something that read quite realistically. We actually sort of tested it out on people, and they couldn't always tell the difference between something written by, say, an undergraduate and the output of the program. Then a few years later, with Ed Ayers, we wrote a program to do what we might call term rewriting, but to find proofs of the form, this expression equals this, equals this, equals this, equals this, equals this, equals this, equals this one, using various rules that you feed the thing. And again, the idea was to have a program that would operate in a reasonably human way. It wouldn't do a big search through a huge tree of equalities. It would, if it was something that a human would find routine, it would tend to just jump from, do the right steps without much backtracking at all. And the key idea there is what we called subtasks. So sometimes there's no sort of obvious improvement. You can't sort of say that if I replace this expression by this one, I'm somehow syntactically closer to the goal. But you can somehow say, well, let's look for a feature that you've got in the goal that you haven't got here that is a nice sort of bottleneck, something where you know that in order to get that feature, you've got to use this replacement rule, and then that splits the problem up. How can we get to a position where we can use that replacement rule and so on? And so all this kind of splitting up the search space using replacement rules to reduce it to an obvious thing, that was what we were doing there. And those sorts of ideas are very closely related to ideas in the literature of AI planning. And then 2 or 3 years ago, I got a grant from the Astera Foundation to set up a group to work on these sorts of ideas. So I've just listed the names of people I've listed here are postdocs and PhD students in the group at the moment. And there are lots of other people who've been sort of communicating with us quite a lot, or have done summer projects with us and that sort of thing. One name I haven't put here, but I feel I should mention, is Matea Jamnik, who, although she's not sort of, I'd say, worked with us, but she's talked a lot to my students and given us lots of very useful advice. And some of the people here are her students, like Mantas Baxis. And several people in this room are on those lists. So this has been really, it's been really nice. I'm very, very happy with the people in the group, and if you've talked to some of them, I think you'll see why. So what were we initially trying to do? We just wanted to, come up with some program that could start from scratch and solve things completely automatically. And in order to do so, we wanted to understand what humans do and maybe develop an actual sort of theory as rigorous as we could make it for what it is. I see the fundamental intellectual problem as we know that finding an arbitrary proof of an arbitrary theorem of length n is an NP-complete problem, so it's just totally unfeasible if you believe that P doesn't equal NP. We also know that mathematicians find long and complicated proofs. The obvious reason for that is that the long and complicated proofs we find are not just arbitrary proofs of arbitrary statements, they're highly structured proofs of interesting statements and so on. What is this structure that makes some pretty complicated proofs feasible for human mathematicians to find? And one component of that would be to develop a theory, sort of say a proof where you can actually explain where the steps came from should be a big component of that. I want to be a little bit careful about the notion of motivated, the word motivated, because it can mean a lot of different things to different people. I've experienced that, and you sort of say, what about this? And then they say, but how do you motivate that? And so on. So I will change terminology in a minute, but anyway, we had to sort of change our aims a little bit because it would have been very hard, even if things had gone as well as possible. Best we could have done would be to come up with fully automated proofs of things that you can type into ChatGPT and get a proof of anyway. So people wouldn't have been interested. So what can we do now that might be interesting? Maybe some people would have been interested. We've done it sort of by hand using an actual algorithm, and you can really understand how the algorithm works. I myself would have been interested, but nevertheless, it was maybe much harder to sell. So what do I mean by a motivated proof? Basically, if I should credit where it's due, I went to some random site on the web and asked it, can you provide a picture of a rabbit coming out of a hat with a red cross in front of it? And that's what it came up with. So a motivated proof is one where you're not allowed rabbits out of hats. I think we all know what that means. There's no sort of step where if you're reading the proof, you say, well, I can understand that that works, but I don't really see where that came from. And the step might be a construction that magically has the properties you want, or it might be some lemma that turns out to be exactly the sort of intermediate lemma that gets you from A to C. It turns out to be quite easy to prove B, and quite easy to prove that B implies C, but it's sort of a mystery how anyone thought of B, that sort of thing. That should be forbidden. And why should it be forbidden? Well, if you think about the search tree, if you're allowed rabbits out of hats, then you can have branches with a huge number of sub-branches. And maybe that's okay if you do it once with a computer, but typically a proof, a sort of long and complicated proof in mathematics, is going to have several steps where you have to do something non-obvious. And if in each one you're allowed a branch like that, then you've got a combinatorial explosion very, very quickly. So what we prefer is something that looks more like this, where it just sort of branches in a rather modest way. And so in the language people sometimes use, we'd like to find a sort of finite action space. So what are we trying to do now? I would say it's dividing the task of coming up fully automatically with proofs into two subtasks. I don't mean the subtask in exactly the sense that I used it with et as, but so one task would be, can we sort of devise a kind of finite action space, a sort of set of moves that one could use when discovering proofs, and so that then the search would be quite a lot more efficient, because you sort of forbid the rabbits, but this finite action space allows you to do moves that generate these rabbits in some way. And I'll talk about examples of that, one example actually, but later on. And then a second question, which either we could work on, or in principle I want this to be sort of approach independent. So once you've got the finite action space, you could then, if you like, try and use reinforcement learning to use that action space in a good way, or you could really think about what moves people take and try and do a sort of explicit program for it and so on. But at that stage, it's sort of put to the side for the time being. So when I say we're aiming for a non-deterministic algorithm, I just mean we're looking for an algorithm where at each stage there may be sort of 2 or 3 options rather than just one, but not too non-deterministic, not like that willow tree with lots and lots of branches. And also I feel as though when I started out, I had this kind of wish to be, or for my group to be the one that sort of solved mathematics and revolutionized it. Now I feel that that's a bit of a silly thing to do. We're competing with some extraordinary people all around the world. So I'd just like to find a niche where we can do something that will be useful to other people or make a contribution. So we've scaled down our ambition. I think actually it's still pretty ambitious, but and yeah, it's not absolutely clear that what we're doing will in the end be worthwhile. It could be that just development in machine learning will just keep on going and will steamroller past us. And actually, even then, I think there's some intellectual value at any rate in trying to understand how humans find proofs. But maybe we wouldn't be able to ever get to the stage where our ideas had helped improve performance on some benchmark. But I'd be okay with that as long as we'd made some contribution that was interesting. So what do I mean by a move here? So what I don't mean, and I want to say this first because I think it's quite important just to stress this, it's not just a step in a proof. That's the, it's supposed to be a step in the proof discovery process. And it's also not just applying a lean tactic, which could be thought of as just condensing a collection of steps of a proof. So particularly, we don't want to think of, when we come up with proofs, we don't sort of do it in the order of the lines of the proof. We do something else. So that's what we want to think about. So instead it's, I'll talk about what I mean by proof discovery state in a moment, but what I mean by a move is, well, perhaps I will just put that up actually. So I'll start with proof discovery state. A proof discovery state I think of as a bunch of statements, including the statement you were originally trying to prove, but it includes a lot of other statements, some of which you've proved in the course of thinking about the original proof, some of which you haven't yet proved, but you'd like to be able to prove, and just some sort of record of how all these things are related. If I could prove this, it would show that this statement here that I wanted was true in the first special, non-trivial special case, those sorts of things that we keep track of as human mathematicians while we're looking for a proof. We have a bunch of statements. We also, for each statement, ideally, have some sort of story about why it's potentially helpful for the original proof, or why if we could answer this question, it might help us to answer that question, and so forth. And then a move is just a way of taking you from one such collection of statements to another one, typically by adding a new statement, maybe sometimes in practice, sort of saying, oh, this question here is not interesting after all, and getting rid of it just to tidy things up. But the main thing is generating new statements from ones we've got. Now again, you could have a sort of computery approach to this, which would be, let's just generate 150 modifications of this statement and sort of check automatically if you can find simple counterexamples and things like that. But that's very much not what humans do, and again, very much not what we want to do, because we want to avoid having this multiple branching. So we want somehow to find out what it is that, it seems that there are very natural choices for how to generate new statements, and that's what we've thought about quite a lot. So here are some types of moves. I haven't said this, but there's going to be some demos coming up very soon of sort of work that people in the group have been doing. And because I'm an old man now, I won't be doing the demos for the people. Anyway, so a lot of these moves go back to, I mean, clearly they're not going to be original thoughts that we have. It's just a sort of, here's a list of types of things that I'm talking about. So even, Poya talked about some of these types of things, and other people have talked about them since. So what I mean by logical strengthening and weakening is taking a statement and replacing it by another statement that is stronger or weaker purely by virtue of its logical form. So if I say A and B implies C, and then I replace that by B implies C, for some particular statements A, B, and C, then that would be a logical strengthening, because I can tell that it's a strengthening, even if I don't care what statements A, B, and C actually were. and weakening similarly. Some of these moves you'll see are more sort of, that's a very well-defined move, or it splits into all sorts of different types of logical strengthening and weakening, but they're all completely possible to define rigorously. Now, I said adding obvious related statements to the context. So one way that I don't want to allow rabbits in out of hats is just to say, consider the following result from sort of deep in MATLib somewhere. Look, it's really helpful, when it's not clear at all how you would have thought of extracting that result from MATLib. That's not allowed. That counts as a rabbit out of a hat. But adding obvious related statements to your context is allowed. And of course, if you ask me, what is the definition of obvious, I can't really give it to you, but I will give you a sort of working definition later on. Choosing the simplest example. Again, in practice, we often know what the simplest example in simple cases of something is. So if you need, at some point in your proof, a positive integer that's not equal to 1, then 2 is going to be your simplest example. And so that sort of thing comes up quite a lot. Spotting patterns and extrapolating from them, that often comes up. Creating metavariables, that's very important. So if your rabbit takes the form, you need an object with some difficult properties to reconcile. Often what you do is create a metavariable. You just don't decide what that object is going to be, but you think, if we were to have an object that had those properties, then you do a lot of reasoning, and you end up, by the end of that reasoning process, simplifying the properties that object has to have, to the point where suddenly you can fall back on just choosing the simplest example or something that has. So we see a very simple example of that when you've got simultaneous equations. You don't just sort of guess what the solution will be and see whether it works, and then have another guess and see whether that works. You do some reasoning, in this particular case Gaussian elimination, and then it becomes extremely easy to write down what the solution is. But something a bit like that seems to take place with much more complicated mathematical object finding. A very important aspect of this is often you make a conjecture that you don't actually believe is true, so that you can find a counterexample, maybe just to see why a particular hypothesis was needed or something. You conjecture that it's not needed, and of course it is needed, but you then find a counterexample. Having found a counterexample, it's not enough just to say, oh, there's a counterexample, so it was needed. You then want to generalize that counterexample to extract as much sort of juice out of the counterexample as you can. And that's something we've actually begun to automate, and one of the demos will be where we are with that. And then obviously the sort of normal moves, the ones that I said were not what I think of as moves, are examples of moves. You know, if you want to sort of use modus ponens, I'm not forbidding that. So that comes in. And the hope there is that we'll get a better search tree. So if your nodes are not proof states, but proof discovery states, are these sort of ensembles of statements that you're working with, and your edges are not write down the next step in the proof or do a logical deduction or something, but generate a new proof discovery state. What drives me is the feeling that that ought to be much more efficient than searching through than the sort of proof graph. So yeah. So that was the one. I very much enjoyed Thomas Hubert's talk, but I felt that that was one thing that he was not quite thinking about. And part of the reason for that is that at the moment, Lean doesn't really support proof discovery states, but all that could be changing. I'm going to call on. So the basic thing we would like to be able to do is actually have some support for proof discovery states. So here's where we are with that. So this is Jovan Gerbshed and Mirek Olsak, two members of the group.
Yes, right. Thank you. Yes, so I will be presenting some various works that I've been doing, some of which together with Mirek and Anand, of creating this better representation of proof discovery states. So to enter the state, I sort of have this combinator, and then I can start typing normal Lean tactics, but there's also some extra things that we've added. So I'll go through this little proof without doing any rabbits out of hats. So we're trying to prove this weak bound of 2 times the cosinus hyperbolicus is at least 1. So first step is we want to rewrite the cosinus hyperbolicus. So let's ask Lin with rewrite question mark. I want to click on this, and Lin gives me a list of what I might want that to be. So this is what it's by definition, but I want it to be this. So I click on it, and the rewrite appears. Now we've got this annoying 2 times and divided by 2, and I can never remember what this lemma is called. So let me call the automation again. So I shift click the expression I want to rewrite, and it gives me a list of suggestions. So you can see here it's sorted by pattern. So the first one is the pattern b times a over b. And then there's the more general patterns for general 3 variables, and then just a multiplication, 2 times something. But the first one is the one that I need. And now there's this annoying side goal 2 is not 0 that appears here, so I can just make that a bisimp to fix that. Right, so what do we do now? So we might remember that the exponent is always positive, so we might want to use that inequality to help us, but I might not remember what this lemma is called, so I will go and find this helpful tool called Lugol by Joachim, and I can write 0 is less than real x of something, and look, there is 1 result. Well, how helpful. And I click on it, and this browser appears where we can see it in context of its file, and it tells us indeed 0 is less than exponent of something. So I'll copy paste that, and go back to the info view. So we want to replace this thing by 0 with something called a generalized rewrite. So you might not have seen this tactic before, but it exists in MATLib now, thanks to the help of Floris, who has been reviewing my PR very helpfully.
It is an unsafe step.
Yes. So, but the problem is, if I just replace this with a 0, that it would be an unsafe step, because it might be that now I'm proving something that is not true anymore. So just in case, I'll make a backup of my state. Right, so, and then I'm doing a generalized rewrite, so we call the GRW tactic, and since our lemma says 0 is less than real x, it's rewriting to the left, so I do a little left arrow, and there we go. So now we see that here our goal state went from this to this. So this is what you can do with generalized rewriting. Right, so now we've got this 0 plus, so we can just sort of simplify, and oh, look, the goal has turned into x is at most 0. Now this is of course a bit of a nonsense goal. We cannot prove this. We cannot prove that for all x is at most 0. But if we assume that x is at most 0, then we can obviously. So let's say assume goal. And what has happened? So the special proof states representation has sort of made, in hindsight, the assumption that x is at most 0. So now we're back at where I made a backup of the state with the extra hypothesis that x is not at most 0. So I can now push the negation at x. All right, and I need to give a name to the new hypothesis, and push neg at hx. There we go. Right, so the new hypothesis then ended hx, and then I push the negation, and now we want to do the same rewrite we did before, except now we want to do this other exponent and turn that into being bigger than 0. So for this we use nth rewrite, because we want to rewrite in the second position. So we do nth generalized rewrites, and then the same. Oh, right, and I need to give the position, of course. So nth generalized rewrite in the second position. And there we go. Now the second one is turned into 0. And this is the same as before, we simplify it. And now the goal is 0 at most x, and we know 0 is less than x. So we simply do a generalized rewrite with hx, and we're done. And all of this passes through the lean kernel, so even though we're doing some funky moves, it's actually verified. Yeah.
Okay. I also talked about automating the process of generalizing proofs. And so now Anand Tadipatri and Angela Gandhi are going to show us some lean tactics.
So we've developed an algorithm that generalizes proofs, like Tim was saying. So it takes in a proof, and it outputs a theorem and a proof that the same proof works for in some sense. It builds on work done in the Rock theorem prover. So for an example of what we mean by this, suppose you prove that the square root of 17 is irrational, and suppose you prove that in the way you'd expect. You assume it's rational, a over b is square root of 17, so on. You'd notice the only fact you really use about 17 in that proof is that it is prime. And so really you should be able to generalize this to a more general theorem that the square root of any prime is irrational. And in fact, that's what our lean tactic does. So you can see here, here we have a lean proof that the square root of 17 is irrational. Then we call our tactic auto-generalize, tell it to generalize the 17 in that above proof. And it adds a new generalized theorem to the context that any prime number has an irrational
So
square root.
you've got a proof that square root of 17 is irrational, but it's very long and I can't see it.
Yeah, it is quite long, so we just put it in. Yes, but this is available on GitHub if anybody wants to check out the proof.
Wait. You have a proof that square root of 17 is irrational, and then you'll do one magic thing, and then what happens? It's just all gone too fast.
So we have a proof that the square root of 17 is irrational.
Handwritten.
Yes, yeah, that we as humans wrote. And the only fact it used about 17 is the lean lemma that 17 is a prime number.
You've inspected the
And-
machine inspected the proof.
Yes, this auto-generalized lean tactic we developed inspected the proof for what lemmas are actually used about 17, or does this actually have to be a 17 in the proof? Yes, thank you. And then lean recognized that this tactic recognized that actually, 17 just had to be prime, and so we can output this more general theorem and its proof adapted accordingly. And yeah, if we need to prove that more general statement, we can close the goal. So I just want to emphasize that this algorithm doesn't derive a more general theorem that the square root of every non-perfect square is irrational, which is also true, but that reasoning step is not evident in the proof term we provided it, so it doesn't come up with that generalization. So this algorithm generalizes the theorem as far as the proof allows, in some sense. So other proof generalizers exist. There is the work we built off of in Rock by Olivier Pont. There's work done by Talia Ringer and colleagues adapting proofs in Rock to work for different inductive types. Most recently, there's work done by Alex Best to generalize lean proofs so that they don't use arbitrarily specific type classes when that's not needed by the proof. And so our work is in this vein. So what have we added? Well, there are two things mathematicians really often do when generalizing proofs that didn't exist in previous software that we've implemented, and that's our ability to generalize repeated constants and dependent constants. So what we mean by this, we'll explain with some examples. So Anand will go through this first one.
So let's say we're in a situation where we have multiple occurrences of a constant in a theorem statement. Like here, where we have square root of 17 plus 17. There are two occurrences of the constant 17, one under the square root and one outside. And it would be suboptimal if the algorithm just placed the hypothesis of being prime on both of these, producing the following generalization. What we would like the algorithm to do is to inspect the proof, realize that the two occurrences of 17 actually play different roles in the proof and produce a more general generalization, which places the hypothesis of being prime only on the occurrence of 17 that used to be under the square root, leaving the other as an arbitrary natural number. And this is something that our tactic does. And here's a demonstration of it in action. So we formalized a proof that the square root of 17 plus 17 is irrational. We run.
Could you switch to a color scheme that actually allows us to see what's on the screen?
Yeah, would you like-
I mean, and even the default one with
Maybe the resolution of the
that is first.
This is the resolution which is. Yes, the resolution.
Is that higher contrast?
It's a little bit, but it's weird. It's better. Yeah, thanks.
Okay. Yeah, so we have a proof here that the square root of 17 plus 17 is irrational. We run automatic proof generalization, telling it to generalize the 17. And we have no other instructions apart from this. And the generalization that pops out is the following, where we have two different natural numbers. One which is assumed to be a prime number, and the other which is an arbitrary natural number. And this is automatically done by that. Over to Anshula, who will demonstrate the other feature that our algorithm implements.
And so this other feature that we'd like a proof generalizer to do is to be able to generalize dependent constants. So, for example, if you have a proof that the union of two sets of size 2 has size at most 4, and you'd like to generalize that 2, you actually have to generalize more than just the number 2 in this proof. You'd have to recognize that this 4 is dependent on the 2's, and it's not a 2 times 2, for example, it's a 2 plus 2. And so our algorithm does recognize that this 4 is actually this 2 plus 2, and that the 2's need not be generalized to the same variable. And so we come up with a more general proof that if you have a set of size n and a set of size m, its union has size at most n plus m. And so we can see this in action. Here we've proven that the theorem with sets of size 2. And then when we tell our tactic to generalize the 2 in that proof, we end up with a proof of a set of size n and a set of size m, and a bound on the size of the union.
And all the examples we've seen so far have involved generalizing numerical constants, but that's by no means the only thing that the algorithm is capable of. As an example, consider Bezo's identity, which is a statement about the integers, which says that the greatest common divisor of two integers can be expressed as an integer linear combination. We formalize this in Lean as the following lemma, Bezo's identity, which says what I just described. And here we won't generalize any particular numerical constant within the statement, but instead we'll generalize the integers themselves, trying to see the most general setting in which the theorem holds. And so we say auto-generalize integers in Bezo's identity, and out pops the following generalization. It's quite complicated, so I'll pull it up for better clarity. But it produces an algebraic structure which is roughly of the same generality as a Euclidean domain. In particular, you can see that there's a size function, taking the elements of the ring and splitting out natural numbers, satisfying a couple of properties that you would expect. For example, the only element of size 0 is 0 itself. There are a couple of other things that the algebraic structure satisfies. In particular, there's a division and a modulus operation, and satisfying a couple of other natural properties. And there are a bunch of other axioms which pertain to the ring axioms. And that's another example of generalization.
So for that one, there wasn't a secret 100-line proof anywhere. Am I right?
There.
I mean, right, but that was in MATLAB.
No.
You did.
We can control click on it.
I see. You wrote this thing.
Yes.
Okay. But what does the proof look like?
Yeah, can you control click?
Is it just a regular? What's going on?
Oh, control
Yeah, that thing just invented.
Because it looks like the system just invented Euclidean domains.
Well, so I guess the key thing to mention is that it wasn't exact. These aren't exactly the properties of a Euclidean domain. It's slightly different, and it's slightly different because the proof is doesn't use it.
But the proof is kosher. There's nothing funny going on.
Yeah, and I guess it's on like our human-oriented ATP GitHub if people want to.
But it wasn't some funny proof that was carefully written in some secret way that made your thing.
It's an honest proof.
Okay.
Yeah.
Yeah. Okay. So Tim is talking about what role is there for human-oriented theorem proving. And proof generalization is something that we do as humans so frequently, we rarely think about it explicitly. And it's something that LLMs are not mimicking, the behavior LLMs are not mimicking consistently. So if you've ever used an LLM to try to collaborate on math with, then you've probably had the experience where you've asked for a proof and you've received an incorrect proof back, and then you prompt the LLM with a counterexample, and then the LLM returns a new proof that is incorrect for the same reason. That is, it didn't generalize the counterexample, it didn't do a proof generalization on the disproof, and use that behavior to adapt its proof. So this is a place where human-oriented theorem proving is really key. And so if you're curious about more details about our implementation of the algorithm, use of meta-variables, unification, anti-unification, the proofs we used and generalized, please see our paper, which will appear in ITP this year.
I wanted to give a quick example of what I would sort of think of as a motivated proof. So I want to start with a non-motivated proof. This is an exercise that came from Herstein's Topics in Algebra. I think it had a star on it, although it's not actually very hard. I have thought about much harder things, examples, but I don't have time to present you a really hard thing. So let's have a look at a proof that every group has a non-trivial automorphism. So 3 cases. If it's non-abelian, then you can find an inner automorphism that does the job. If it's abelian, then either every element is equal to its own inverse, in which case it's known that it must be f2 to the n, and because the size of the group is bigger than 2, the dimension is bigger than 1, so you can sort of swap the first 2 coordinates. Or there's an element that's not equal to its own inverse, and then the map that takes each thing to its own inverse is an example of a non-trivial automorphism. Okay, so an awful lot of rabbits there. Why did I do that? Actually, sorry, there's 3 cases. I forgot to adjust the slide. So why did I split into those 3 slightly complicated-looking cases? Why did I sort of think about inner automorphisms? Where did the map, let's map each x to its inverse come from? And where did this idea of looking at f2 and f2 to the n and so on, where did that all come from? Just an analogy I like is sort of with NP problems. So there are a lot of these things where if you're given the sort of the thing, you can check quite easily. You're given the idea, it's easy to check that it works, but the whole point is where does the idea come from? And as I say, well, in this case, it's not that hard to see where the ideas come from, but I just want to highlight the process a bit. So, so where did the idea of inner automorphisms come from? Just the fact that those are the most basic examples. I would say this is choose the simplest example. It's the most basic sort of automorphisms that one learns about are inner automorphisms. So once you've had that idea, you add the idea of inner automorphisms to the context, you create a new conjecture. Perhaps every group has a non-trivial inner automorphism. Every group of order greater than 2 has an inner automorphism. So I create a new conjecture that that's the case. Of course, it's a false conjecture, but it doesn't matter. I can sort of add it to my proof discovery state. I unfold the definition to see exactly what that means, and I find that I need, I think at the bottom there, I need to find an x and a y such that the conjugate of x by y, no, y by x is not equal to y, and that can be simplified to get rid of the inverses. And I see actually that I just want the group not to be abelian. So I refold this definition, and I get I want the group to be not abelian. So my new conjecture by that stage is every group of order greater than 2 is non-abelian, and that is just false. Then we can, once we know that it's false, we can do something very similar to what Jovan did in his demonstration. At the very least, we have proved the result for non-abelian groups, and so we now are free to choose, to add as a hypothesis that the group is abelian. So there's the new problem. For every abelian group of size greater than 2, there's a non-trivial automorphism. So now let's just take these targets here Of course, you still want to keep the hypotheses, but just for ease of presentation on the slide, I'll just concentrate on the targets. We need these properties to hold of some map from the group to the group. And so when I look at this, I've got this funky new hypothesis that the group is abelian. I don't really know what to do at this stage, but I might as well just use that hypothesis somehow. And maybe I would swap x and y here and swap x and y here, and then realize that I'm back where I started, so that wasn't helpful. But after a short time, I realized that perhaps if I just swap it around on one side, I've actually swapped it on the right, I'll get something genuinely new. So I look at this, and then I see, oh, that's a sort of interesting looking pattern where it's like a homomorphism, but it goes the other way. Actually, I think I know an example of that, and that's, I've seen this theorem that ab to the minus 1 equals b to the minus 1, a by a to the minus 1. So that sort of pops into my head in a natural way. So we could try that. And then we see, yes, that works. You've got an automorphism. But we need to make sure that it's not a trivial automorphism. So we need to find at least some x that's not equal to its own inverse. And in fact, that's not true. There are groups like C2 cross C2 for which that statement is false. That there are elements, there's groups where every element is equal to its own inverse. Having got that counterexample, we stick it into auto-generalize. Now, there's a little bit of a qualification. I don't know whether, I think auto-generalize is not quite capable of doing this. This is sort of future work, but near future work. So, for example, a technical problem here is that C2 cross C2, the real constant you want to generalize is a 2 that's that doesn't appear there. It should be C2 squared, and it's that squared that we want to generalize to C2 to the n. Also, the proof itself might be totally unhelpful. You might just look at the multiplication table of C2 cross C2 and just observe that every element is its own inverse. So sort of down the diagonal, we've just got identity. So you have to write the proof in as abstract a form as you can somehow. You sort of pick an element, it must be, as you think of as a function from 1, 2 to C2, etc., etc. And then if you write the proof in a sort of, if you get into the habit of writing all your proofs in a way that might make them amenable to generalization and auto-generalization, auto-generalize is much more likely to work, of course. I think probably if you do present it with the n explicitly, I mean, the exponent 2 explicitly there, probably auto-generalize would be capable of it, or maybe sort of little technical problems, but basically. So then, what is the optimistic conjecture? That's so we've generalized the counterexample as far as we reasonably can and said it's false for C2 to the n. One other sort of proof discovery move is once you've proved something, once you've got a counterexample, you just sort of optimistically assume that's the most general counterexample there is. We all do that the whole time, you know, sort of, but somehow it's not worth doing until you've really made an effort to generalize and then sort of tidy up the generalization so that it becomes a natural statement, and its negation is also a natural statement. And so that's also those kinds of processes are things that we're thinking about a lot. So now you end up with a conjecture that if every element is equal to its inverse, or equivalently, if every element squares to the identity, then it must be C2 to the n for some n. Now the thing I want to highlight here, we all know this result, but the thing I want really to highlight is that we've ended up with a conjecture that was not at all apparent in the original problem statement. So we've used very, very mechanically sort of moves and ended up with sort of just generating some conjecture that is a sort of nice fact. So another sort of thing that I believe is that that's sort of a huge part of how mathematics develops. People often say, will machines actually be able to ask interesting questions? And I think the answer is yes, they'll use this sort of method to ask them. And also, we've seen this sort of, can they ever invent a new concept? In principle, yes, they can invent Euclidean domains or something similar to Euclidean domains. So, well, I think I won't tell because I'm a bit short of time. The rest is pretty straightforward, how you actually find an automorphism in the case of C2 to the n. I just want to highlight a couple of things. This step of thinking of inner automorphisms, I do a sort of ChatGPT test. So I ask ChatGPT, what are some examples of group automorphisms? The first thing it says is inner automorphism. So I think that sort of is a proof that it wasn't an unreasonable step. A similar thing. What about this standard observation that C2 to the n can be thought of as F2 to the n as that vector space? When I gave that prompt, after I'd read all the "that's a wonderful question, how very interesting" and so on, we got to this. You can think of it as an n-dimensional vector space over F2. And it even actually would have helped me cheat and sort of talked about the automorphism group of C2 to the n. I didn't ask it for the automorphism group, but it did actually give me that. So if we're thinking about, one of the things I want to do is not, if there's something that ChatGPT can already do well, then we're not going to sort of struggle to produce some handcrafted version of the same thing. But some of these sort of fuzzier steps, I think, are things exactly that machine learning is good for. And finally, what about this thing where I said you recognize that pattern? Well, ChatGPT certainly recognized the pattern and gave me all this almost immediately. So just to conclude, these are some of the things we want to do. I've sort of talked about them. We would like to, a lot of other people have talked about how nice it would be if you could have a tool where you actually used it while finding a proof and not just to formalize it once you've found it. And so we would very much like to do that sort of thing. I did have another demo, but I clearly have not got time for that, so I'd better hand over to questions. Yeah.
Questions for Tim? Michael?
Now, on the back wall here, there's a picture that was taken in this room 32 years ago this month, and it shows Andrew Wiles with a big smile on his face standing in front of a rabbit. But if you know the story, you know that the last step in his series of 3 talks was in some ways the most surprising of all. And I've been told that Serre particularly appreciated this rabbit and rabbits more generally. So I'm wondering where you think the rabbits actually do fit in with this program.
I think the rabbits are just what you get when you hide all the non-rabbity part. So I just, Wiles took 7 years. He was doing something during those 7 years. He wasn't just sitting at his desk waiting for the rabbit to jump up there.
This was, I think, in the last month or so before he made his announcement. He'd been sitting for 6 years and 11 months and was stuck. And then this.
It was the last rabbit.
What?
It was the last rabbit.
It was
The 3-5. You're talking about the 3-5 switch,
which turned out actually, upon further examination, to have been a very, very fruitful idea. That
So there are some mechanisms by which you can have rabbits. You can just do a fairly big search and get lucky at some point, and then you have got something that looks like a rabbit. But I have a sort of conviction that.
I think you should. He had a theorem that worked for all primes, and he tried to use 3, and it didn't work. And then the rabbit is, why don't we try 5? So,
Next simplest example.
than that, no.
I didn't say that this choose the simplest example can be iterated.
right.
Heather?
I completely agree. It's very nice to have sort of a discussion of how to discover proofs. But have you thought about, once you have discovered the proof, rewrapping it into a rabbit proof? Because there is an advantage to that. It can be checked very fast. And sometimes what we like is a very quick way to convince our colleagues that the proof is correct without necessarily explaining to them how it was invented.
Yes, so, I mean, that's a good point. So once you've found a proof using these proof discovery states, you'll have a whole lot of junk, all these kinds of, but if the proof discovery, I mean, with some mechanical system, it should be possible to keep track of all this junk and what was needed and what wasn't needed, and at the very least extract a sort of minimal tree from the junk that ended up with a proof. That might not necessarily be the neatest proof, and in practice with human mathematicians, very often the first proof they discover is very far from the neatest proof.
But I feel like sometimes the best way to convince someone that the proof is correct is to reintroduce the rabbit.
That may very well be the case. And so I suppose I would say my angle on this, I'm not coming at this from as a formalizer, and so convincing somebody that the proof is correct is not my top priority. Again, I'm very happy that other people are coming at it from that sort of angle. And you know, this would, I hope, be our contribution and other people, if we could produce these sort of rather complicated things. I think it's a very, very interesting project to sort of extract from that the sort of most human-friendly output that you can.
Yeah, Kevin.
So, haven't people pointed out that one of the problems with the literature is that it's often pared down so that it looks like rabbits, and all the discovery process is removed.
Yeah, so this is something that I was,
Is that
again,
what Gauss did, right? He was the fox who was facing his tracks.
yeah, so this was something that Thomas Ubel didn't
Right.
say. So he said we need more data. But what he didn't say was we need a different kind of data. And that's what this last thing here is, one of the things we'd like to do is actually produce data that might be better for training, training all sorts of systems, where we actually have proofs with carefully labeled moves that have been done at each stage. So we have plans to try to produce such a database. Waiting to hear whether we have funding to implement those plans, but watch this space.
But I think it's related to this because what I wanted to ask is that how do mathematicians do mathematics is an empirical question. And the sort of Polya approach of introspection, I think, is very successful. Right? Polya identified a huge number of heuristics and bits of plausible reasoning for how to do things. But are you concerned at all that this sort of method will leave out things that other mathematicians use in their day-to-day life? Or how do you intend to approach the empirical question of actually getting all the moves that mathematicians use?
Now that is a problem, and I think it's quite likely that because that we don't have domain expertise in all branches of mathematics, that there'll be moves that, I feel as though the moves that an algebraic number theorist or a category theorist would do are very different from the moves that I would do. So the moves that would naturally occur to me, I sort of find problems in these other areas, they look very scary to me, and I think that sort of feeling is mutual somewhat. I think it is there is that danger of just missing out on what some moves, but if more people were to get involved, or if we just produced something that was pretty good at problems in certain domains, but was not so good in other domains, I would be very, very happy with that. And with any luck, that would be a sort of proof of principle, and other people would get interested in saying, well, great to see how it did in graph theory, but what a shame that it can't do algebraic number theory. But if we did this and get people interested in that way.
Just one last question.
Yeah, in a way, these rabbits out of a hat is probably just a perspective, right? It's not so surprising, it's not a rabbit out of a hat for the magician. I'm more worried about the rabbit holes, where you get stuck in something and you try and you don't really see, actually, this is a dead end.
Yes, there would need to be some, if you want to start automating it, you've got to have some way of organising your search so that you don't just sort of produce more and more statements and get into a complete mess. But that's the sort of, we humans have to make those kinds of decisions a lot. Sort of, at what point do you say, I'm bogged down, I'm going to stop? That's somehow part of the sort of second, in the divide and conquer strategy, the sort of second part that we're not concentrating on at the moment. At the moment, we're providing you with the tools to go down a rabbit hole and get stuck, but not giving you advice about what to do.
But you stop and do something else, right? That's the...
Yeah, exactly. Well, that's which I apparently said about 20-something years ago.
Cognitive scientists sometimes call that metacognition, kind of inspecting the procedure and realizing you've just gone off. Okay, well, let's thank Tim again for a wonderful talk.